And we're going to get into talking about sound here, which is a particular kind of wave. You might already know this, but sound waves, transverse or longitudinal, well, turns out they are longitudinal. They're vibrating air. If they're traveling through air, they could be compressing and rarefacting air molecules. Or if sound, say you bang on the desk, then you've got the molecules in the desk that are compressing and then expanding. So sound waves travel through that, but the displacement of a particle is in the same direction as the wave is traveling. So if the wave is traveling that way, then the particles will vibrate and go whoop, whoop, back and forth that way. The speed of sound depends on the medium, what it's traveling through. In air at 20 degrees Celsius, 1 atmosphere pressure, speed of sound is about 343 meters per second. Page 460 has speeds of sound in other materials. Generally speaking, the speed of sound is greater in solids, and then is greatest in solids, I should say, and then least in air and other gases, and then in between in liquids. So the speed is dependent on the density of the material. Sometimes, although air, as it gets warmer, sound travels faster because the air already has more kinetic energy. So so it's not unilateral, but speed of sound in solids is definitely faster than it is in liquids. Just as a point of reference, light is a heck of a lot faster. Light is another kind of wave. Speed of light is 3 times 10 to the 8th meters per second. That's almost 1 million times faster than the speed of sound, which is interesting. That's why in a storm you can figure out how far away lightning strike was by counting the amount of time between seeing the thunder and hearing the lightning. Sorry, I said that backwards. Seeing the lightning and hearing the thunder. Also, I don't know if you've ever really thought about this, but thunder, what is thunder? Well, when lightning zips down through the air, it ionizes the air molecules and basically zaps everything that's in its path and temporarily creates a vacuum. And then thunder is just the air rushing back in to fill up that vacuum. So, say a lightning strike is a distance d away. Well, that distance is going to be equal to c, the speed of light, times the time the light takes. And this is really, really big, 3 times 10 to the 8th meters per second. That is ridiculous. That's 30,000 kilometers per second. So if you can see it, the time it's going to take you to see it is pretty much 0. It's going to be negligible. So then the distance is just going to be then velocity of the sound times the time it takes you to hear it, the distance it travels away. So that's going to be 343 times time. So if you count 1 second, then you're about 350 meters away. If you count 2 seconds, you're about 700 meters. So about 3 seconds-ish. Every 3 seconds is about more or less a kilometer. So that's you can use that next time there's a storm, and it's just an interesting way of figuring out how far away the lightning strike was, where this is the time in between you see it, you start counting, and then about every 3 seconds is a kilometer of distance away. Another interesting effect of the difference between the speeds of light and sound comes in at sporting events. This particular problem is in reference to a baseball game. So you got a fan in the left field stands who's 110 meters from home plate. So the sound of the bat hitting the ball will travel straight to him. So how long? Well, the question is, who hears the ball first? So 110 meters, that's a simple one. Distance is equal to velocity times time. So 110 meters away, and we'll say that's at about 343 meters per second. We can see then the time that it takes is about 0.32 seconds. Now, meanwhile, consider somebody who's watching the TV at home. Sound travels to a microphone that is 8.4 meters behind home plate. So time is distance over velocity. So we go 18.4 meters at speed of sound. That's the time it takes to travel that distance, where it is converted to a radio wave that travels 4,824 kilometers at the speed of light. So distance, kilometers, add 3 zeros, over velocity, 3 times 10 to the 8th. That's how long it spends as a radio wave. And then it's converted back to sound. The speakers are 1.8 meters from where the fan is sitting, so then we go travel at the speed of sound, another 1.8 meters. What do we get for that? So 18.4 plus 343 plus 4,824,000 divided by, 3 times 10 to the 8th, plus 1.8 over 343. And I made a mistake because I did something. What did I do? Oh, sorry. I just took 18.4 plus 343 divided by. Okay. So time here is 0.075 seconds. So that's an interesting fun fact that the person at home will be the one who hears the sound of the bat first, before someone who's sitting in the left field bleachers. In fact, if we take that amount of time multiplied by the speed of sound, if a person is more than about 26 meters away, the person at the park is more than about 26 meters away, the person at home will hear stuff first. It's interesting, an interesting phenomenon. Also, if you're at a baseball game and you're in the outfield, you can see you can noticeably see the bat hit the ball before you hear it. Here's another good one. You drop a stone into a well at 7.35 meters deep. How long does it take you for you to hear the sound? Well, we know distance is equal to speed times time for the sound, but we've also got the drop time, so for which we have to use kinematics. So the time it takes to drop down into the well, it's just falling, so we've got that, and then for the sound to then travel back up, we've got 7.35 is equal to the speed of sound times the time it takes for the sound to go up, and the total time is the sum of those two. So the time it takes for the rock to drop down is about 1.22 seconds. And then the time it takes for the sound to come back up is pretty small, 0.021 seconds. So how long does it take for you to hear the sound? Well, it's just the sum of those two. We add them together, and we get about 1.25 seconds that it takes you to hear the sound. For sound waves, the different physical properties that the waves have corresponding terms that relate to our hearing. So what physical properties do waves have? Well, we know frequency. Frequency is one property of sound. Some of these things you guys might already know. The frequency of a sound, especially you musicians, you probably know a lot of these things. Frequency determines the pitch of a sound. High frequency means high pitch. So when I talk like this, I am producing low frequency waves. And when I talk like this, I'm producing higher frequency waves. Remember, frequency is 1 over period. The unit for that is inverse seconds or 1 over seconds. That is also known as a hertz. Just as a reminder, the range of human hearing is from about 20 to 20,000 hertz. That varies slightly from person to person. And actually, kids can hear higher higher frequencies than adults can, children can. And of course, as you probably know, like dogs can hear higher frequencies than people can, and so forth. For any of you who are musicians, middle C on the piano is about 262 hertz. High C or soprano C is about 1047 hertz. For those of you that are musical, that might give you a frame of reference. For me, it is meaningless, but if that helps you get a gauge, then hooray. Frequencies below this range are called infrasound. In nature, and this is just kind of some interesting information. This one probably won't show up in an AP exam, but both elephants and whales use infrasound to communicate over long distances. Elephants make infrasonic noises with their trunks that can be heard for about 200 kilometers away. Other elephants can hear these sounds, they say. And whales in the ocean make infrasonic things that they say other whales can hear thousands of kilometers away. It's pretty cool. Lower frequencies travel farther while maintaining cohesion than higher frequencies, which is why these can travel far away. Frequencies above this range are called ultrasound, which you're more likely to have heard of that term. Bats and dolphins, and this you probably know, they use echolocation. They let out a series of high-pitched clicks. Well, these are ultrasonic clicks that then bounce off of bugs or fish and allow these animals to locate their food. It's the same principle that people use. Sonar, which stands for sound, navigation, and ranging. Sonar on submarines and whatnot also use ultrasound. Medical imaging is another application of ultrasound. You might have had an ultrasound if you sprained your ankle or whatever. It's a way of imaging bodily tissues. So that's just some interesting uses of sound.